Hi everyone. Today we're going to study combining relations. Relations from set A to set B are subsets of Cartesian product A times B. Therefore, two relations from A to B can be combined in the same way as we do the set operations. Let us see this example. Let set A with elements 1, 2, and 3 and set B with elements 1, 2, 3, and 4. While the relations R sub 1 equals ordered pair 1, 1, ordered pair 2, 2, and ordered pair 3, 3. And relation 2 with ordered pairs 1, 1, 1, 2, 1, 3, and 1, 4 respectively. Let us evaluate the following. Starting with R sub 1 union R sub 2. We're going to combine all the ordered pairs of the two relations. For repeating ordered pairs, we're going to write it only once. So the elements are 1, 1, 1, 2, 1, 3, 1, 4, 2, 2, and 3, 3. Next, R sub 1 intersect R sub 2. We're going to write the common ordered pairs of the two relations. And there is only one ordered pair, which is 1, 1. So we write it here. Next, R sub 1 minus R sub 2. We're going to write all elements of R sub 1 that do not belong to R sub 2. The elements are 2, 2, and 3, 3. Next is R sub 2 minus R sub 1. We will write all elements of R sub 2 that do not belong to R sub 1. The elements are 1, 2, 1, 3, and 1, 4. Then the exclusive OR, R sub 1 XOR R sub 2. We're going to write all elements of the two relations combined, except the common ordered pair. So we will write here 1, 2, 1, 3, 1, 4, 2, 2, and 3, 3. Take note, we exclude the 1, 1. Today we're going to study inverse and complementary relations. Let's begin with a definition of inverse relation. Let R be a relation from the set A to the set B. The inverse relation from B to A, denoted by this symbol, we read this as R inverse, is the set of ordered pairs BA such that AB is an element of R. Let us define complementary relation. Let R be a relation from the set A to the set B. The complementary relation R bar, or sometimes we read this as R complement, from A to B is the set of ordered pairs AB, such that AB is not an element of R. Let us see this example. Let set A with elements 1, 2, and 3, set B with elements 1, 2, 3, and 4, and set C with elements 0, 1, and 2. The relations are from A to B, This is R equals 1, 1, 1, 4, 2, 3, 3, 1, and 3, 4. And relation S from B to C. S equals the ordered pairs 1, 0, 2, 0, 3, 1, 3, 2, and 4, 1. Let us evaluate the following, starting with the R inverse. So we're going to interchange the position of the first element and the second element of each of the ordered pairs. So the elements of R inverse are 1, 1. This 1, 4 becomes 4, 1. 2, 3 now becomes 3, 2. 3, 1 becomes 1, 3. And 3, 4 becomes 4, 3. For the S inverse, the same idea we will do. To interchange the first element and second element of each of the ordered pairs. So 1, 0 becomes 0, 1. 2, 0 becomes 0, 2. 3, 1 becomes 1, 3. 3, 2 now becomes 2, 3. 4, 1 becomes 1, 4. Next is the R complement. In taking the complement, take note that the universal set equals the Cartesian product A times B. For the elements of the complement, we're going to write all the elements of the Cartesian product that do not belong to the relation R. So the elements are 1, 2, 1, 3, 2, 1, 2, 2, 2, 4, 3, 2, and 3, 3. Now for the S complement. Take note that the universal set is the Cartesian product B times C. So the elements are 1, 1, 1, 2, 2, 1, 2, 2, 3, 0, 4, 0, and 4, 2. This is the final answer. Today, we're going to study composite and powers of relation. Let us define composite relation. Let R be a relation from the set A to the set B, and S a relation from the set B to the set C. The composite of R and S is the relation consisting of ordered pairs AC, such that AB is an element of R and BC is an element of S. We denote the composite of R and S by this symbol. We read this as R composite S. Example, let set A with elements 1, 2, and 3. Set B with elements 1, 2, 3, and 4. And set C with elements 0, 1, and 2. The relations are from A to B with elements 1, 1, 1, 4, 2, 3, 3, 1, and 3, 4. And relation S from B to C. The elements are 1, 0, 2, 0, 3, 1, 3, 2, and 4, 1. Evaluate R composite S. For our solution, let us write this R composite S. We say that let us map each ordered pair of relation R, and this is AB, to ordered pairs of relation S, which is BC. You can notice that the second element of ordered pair from R, which is B, must be the first element of the ordered pairs of S. If that is so, we're going to write AC, the first element of R combined with the second element of S, which is C. Now let us start by the first element of R, which is 1, 1. We can map this to the element of S, which is 1, 0. Again, the second element 1 here is mapped to the first element of 1 in here. Then we will match the 1 and 0 together. So the first ordered pair will be 1, 0. Next, the second ordered pair 1, 4. Mapping this 4 to the ordered pair of S, we have this 4, 1. And then we will combine this number 1 and number 1. So we have here 1, 1. Third ordered pair is 2, 3. We can see that there are two ordered pairs from S that starts with 3, which is 3, 1 and 3, 2. Therefore, we're going to write 2, 1, also 2, 2. Next ordered pair is 3, 1, and we can map this to 1, 0. Then we can combine the ordered pair 3, 0. The last ordered pair is 3, 4. We can map this to the ordered pair 4, 1, so we can write this 3, 1. This is now the final answer. Let us define powers of relation. Let R be a relation on the set A. The powers of relation denoted by R raised to n, where n equals 1, 2, 3, and so on, are defined recursively by R with power 1 equals R, and R raised to n plus 1 equals R composite R raised to n. This definition shows that R squared equals R composite R, and R cubed equals R composite R squared. Let us see this example. Let R equals the ordered pairs 1, 1, 2, 1, 3, 2, and 4, 3. Find the powers R raised to n, where n equals 2, 3, 4, and so on. For our solution, let's begin with R squared. By definition, this is R composite R. We're going to map R by itself. Let's begin with 1, 1. Let us look for ordered pair that starts with 1, and it points out to the same ordered pair 1, 1. So we can have the first element to be 1, 1. For 2, 1, it will come to this 1, 1, and eventually we will have 2, 1. For 3, 2, it will point out to 2, 1, and eventually we will have 3, 1. For 4, 3, it will map to 3, 2, and eventually we will have 4, 2. So these are the elements of R squared. Also, for the R cube, we will have R composite R squared. So this 1, 1 will map to 1, 1, and we will have the first element 1, 1. This 2, 1 will map to this 1, 1. Eventually, we will have 2, 1. This 3, 2 will map to 2, 1, and eventually we will get 3, 1. This 4, 3 will map to 3, 1, and eventually we will get 4, 1. So these are the elements of R cubed. If we continue for the R with power 4, we will see that r power 4 is simply the same with r cubed, and so is the remaining powers of r. Therefore, this r raised to power n is equal to r cubed. This is the final answer. I hope you learned something from this video. See you again next time.